I welcome you all in this lecture on waveguide junctions. Today we'll discuss waveguide junctions. We'll also try to describe a set of parameters called as S parameters. We'll also see why we use S parameters at microwave frequencies, and why not the other parameters like Z parameters, Y parameters, ABCD parameters, or H parameters, etc. So at microwave frequencies, we prefer S parameters over these parameters, Z, Y, ABCD, or H parameters. Now, first thing that we'll discuss is waveguide junctions. So what are waveguide junctions? Waveguide junctions are basically passive microwave components. They're passive microwave components used for combining or splitting microwave power. So they're passive. First thing is that they are passive microwave components. Now, as you know, electronic circuits are made up of two types of components. We have two types of components. We have active components and passive components. So let us see what are active components and what are passive components. This is something that you have already read in your previous semesters, but just to recapitulate it. You know, an active component supplies energy to an electric circuit. Supplies energy to an electric circuit, and hence has the ability to electrically control the flow of charge. So what are the examples of active components? Common examples are, voltage sources, current sources, transistors like BJTs, FETs, MOSFETs, etc. BJTs, FETs, JFETs, MOSFETs, etc. MOSFETs, etc. These are the common examples of, active components. The second class of components, as you know, are called as passive components. So what are passive components? Passive components, can only receive energy. They can only receive energy, which they can dissipate, absorb, or for that matter, they can store it. So examples of passive components are examples. Resistors, inductors, and capacitors are all passive components. They receive energy, they either dissipate it, store it. That's it. So the second category, as I said, are passive components: resistors, inductors, capacitors, even transformers are passive components. Transformers are also passive components. This is because they are either used for stepping up or stepping down voltage. But the power and energy, so far as power and energy are concerned, power and energy remains the same. Power and energy remains the same. One second. Power and energy in case of transformers remains the same on primary and secondary sides. On primary and secondary side. So this is just a recapitulation of the electronic circuit components, active components, and passive components. Now, so far as our waveguide junctions are concerned, I said they are passive. We are interested in discussing waveguide junctions. Junctions, so they are passive components used for, as I said, either combining or splitting the microwave power. So in power splitting mode, an input signal is divided into two or more signals of lesser power. They are divided into two or more signals. A single signal in power division mode is divided into two or more signals of lesser power. For example, let's consider a simple waveguide junction. This is a simple waveguide junction. It has three ports: port 1, port 2, and port 3. Say, for example, a signal is fed at port 3. This is the signal that we feed at port 3. So naturally this signal will split into two parts, one part and second part. So if we are connecting a source at port 3, part of this energy or part of this signal flows to port 1 and part of this energy flows to port 2. So this time it acts like a splitter. So this waveguide junction in this example acts like a splitter. So other case is that we can even combine signals using a waveguide junction. For example, if I use the same junction, 3-port junction, by the way, this 3-port junction resembles the English letter T. It is also called as a T junction. Now in power combining, what will happen is that if I feel this is say, for example, this is our port number 1, this is our port number 2, and this is our port number 3. Now if I connect a source at port 1, another source at port 2, so these two signals will add up and the resultant signal, the addition of these two signals will add vectorically. That is the addition or that is the resultant wave is the vector sum of waves arriving from ports 1 and 2. If the two signals reach in phase, then the signal coming out of port 3 would be the signal at port 3 is the algebraic sum or the vector sum of signals coming from ports 1 and 2. So the addition basically depends on the phases of the two individual signals. So if the two signals reach at a point in phase, they will simply add up, or if they are out of phase, the resultant signal would be having a minimum amplitude or energy. So this is how they are used for adding or splitting signals. This is what waveguide junctions are meant for. They are either used for combining microwave energy, or they are used for splitting microwave energy. Now let us see an analogy of a microwave junction. Say for example a microwave junction or a waveguide junction. A waveguide junction is analogous to a junction of water pipes. Say for example we have a pipe carrying some water, and then at some point it is being split into two pipes. So the water coming from port, say for example 3, splits into two ports 1 and 2. Or for that matter, water coming from ports 1 and 2 can add up and come out from port 3. So this is simply the addition of two water waves, or splitting of water from a single pipe to different pipes. So this is what waveguide junctions primarily are meant for. Waveguide junctions also split a microwave signal into two or more signals, or combine two or more signals to a single signal. So for as the network theory is concerned, we use a set of parameters for describing these passive components or for describing networks. See, it's well known that linear time invariant circuits are completely described by some parameters like Z parameters, Y parameters, H parameters, ABCD parameters, etc. But at higher frequencies or at microwave frequency, we use a different set of parameters called as S parameters for describing networks. So again, we use these S parameters for describing waveguide junctions. Now, before we describe S parameters, or before we define S parameters, we'll revisit the parameters that you have used in your lower semesters, the parameters that you have used at lower frequencies. Let us recapitulate Z parameters. Say for example, if we have a two-port network, this is a two-port network. This is port 1, this is port 2. Let us assume this voltage is V1 and this current is I1. This voltage is V2 and this current is I2. So current entering port 1 is I1, current entering port 2 is I2, voltage at port 1 is V1 and voltage at port 2 is V2. So the relationship between these voltages and currents in terms of Z parameters is V1 is Z11 I1, Z12 I2. V2 is Z21 I1 plus Z22 I2. So where V1 and V2 represent the total voltages at V1 and V2, I1 and I2 represent the total currents at ports 1 and 2. So in matrix form we can write it as V1 V2 is equal to Z11 Z12 Z21 Z22 I1 and I2. So if we can find, or if we know these Z parameters, we can completely describe this network. So this is what we have done in the previous semesters. So if we know Z11, for example, Z11 in this case would be V1 upon I1 when I2 is 0. So this means I2 has to be 0 and I2 will be 0. That would mean we have to create an open circuit at port 2. So for determining Z11, we have to find the ratio of V1 and I1, but the condition is that we need to open circuit port 2. Likewise, we can find, for example, Z12 as Z12 would be V1 upon I2 when I1 is 0. So the ratio of V1 and I2, but the condition is I1 has to be 0. I1 would be 0 would mean that we need to create an open circuit at port 1. So likewise, we can describe a network by using Y parameters. In case of Y parameters, you know the relations are I1 is Y11 V1 Y12 V2, I2 is Y21 V1 plus Y22 V2. We can find Y11 like by using this relation. Y11 is I1 upon V1 when V2 is equal to 0. So in this case, the ratio of current I1 at port 1 to voltage at port 1, the condition is that V2 is equal to 0. So V2 is equal to 0 would mean we have to create a short circuit at port 2. So this is how we define these parameters. And these parameters, if we know these parameters, Z parameters, Y parameters, etc., we can describe the linear time invariant system or the network which is of our interest. Now, but at microwave frequencies or at RF frequencies, greater than 100 megahertz, we prefer S parameters over ABCD parameters, Z parameters, Y parameters, etc. for describing the network. So at higher frequencies, what we do is that, as I said, we talk of S parameters. So how are these S parameters different from ABCD parameters, Y parameters, Z parameters? We'll see that. S parameters basically relate the incident voltage waves on the ports to the reflected voltage waves. See, these S parameters so far are concerned, they relate the incident and reflected waves. Incident and reflected waves. Say for example, I have a single port network. There is only one port. I'm applying some source here. So from the source, a wave will move towards the junction. Now if this is perfectly matched, then there won't be any reflections. But if this junction is not perfectly matched, then there will be a reflected wave as well. Just to tell you, if I have a transmission line and I am connecting some load to it, if this load impedance is ZL and the characteristic impedance of transmission line is Z0, if Z0 is not equal to ZL, so what happens is that a wave which moves towards the load gets reflected. So part of the energy gets reflected back towards the source if this is a source. So if I connect a source to a load via transmission line, if ZL is not equal to Z0, there would be reflections. If otherwise Z0 is equal to ZL, the transmission line characteristic impedance is equal to load impedance. This is the load impedance, this is the characteristic impedance. If Z0 is equal to ZL, then the whole wave, the total energy gets absorbed in the load. There are no reflections, no reflected wave in this case. Likewise, if I am connecting a network, say for example here, to a source as shown here, so what happens is that if this load impedance is not equal to characteristic impedance, then there will be surely reflections. So this is how we define these S parameters. So in case of S parameters, let's consider a two-port network. Say for example, we have a two-port network. This is port 1 input port and this is port 2, which is output port. This is a two-port network. So if I connect a source here, a wave moves towards this port and some part of the energy in general will be reflected back. So let us designate the input signal by A1 and the reflected by B1. So A1 corresponds to the incident wave, B1 corresponds to the reflected wave. Likewise at port 2, A2 corresponds to input and B2 corresponds to reflected wave. So how are these incident and reflected waves related to each other? They are related by a similar matrix, like the Z parameters relate voltages and currents, Y parameters relate currents and voltages. These relate the reflected and the incident voltages. See, for example, this is the reflected, B1 is the reflected wave here, B2 is the reflected wave here. So B1 and B2 are related to the incident waves A1 and A2 by a set of parameters called as S parameters. So in equation form we can write B1 is S11A1 plus S12A2. B2 is S21A1 plus S22A2. So if I have to find, for example, S11, so S11 would be B1 upon A1 whenever A2 is equal to 0. Likewise, S12 would be B1 upon A2 whenever A1 is equal to 0. So we'll see them as we go down the line. So this represents the reflected wave. B1, B2, they represent the reflected waves, and A1, A2 represent the incident waves. So the question now is, why do we use S parameters? Why S parameters? So before we discuss this question, why S parameters, just try to tell you that these S parameters, they represent the reflected and incident waves. As for example, S11 is B1 upon A1, S12 is B1 upon A2. As I said, A1 and A2, they correspond to incident waves, and B1 and B2, they correspond to reflected waves. So we are discussing it in terms of waves rather than voltages and currents. In case of ABCD parameters, Y parameters, Z parameters, the discussion is in terms of currents and voltages. But here, when it comes to S parameters, the discussion is in terms of the incident and reflected waves. So why S parameters? The first important reason is that, as I said, for finding Y parameters, the low frequency parameters, the parameters that are used at lower frequencies, usually, for example, for finding Y, Z, H, or for that matter ABCD parameters, as I said, we need to open or short circuit. We need open or short circuit at the ports. As said already, for example, Z11 here, Z11 is V1 upon I1, I2 is 0. So we need to create an open circuit at port 2 for getting Z11. Or again, for finding Z12, we need to create an open circuit as I1 is 0. Likewise, if I try to find Y11, we need to create a short circuit, V2 is 0. So for determining these parameters, Y, Z, or ABCD, whatever, we need to create open or short circuits at the ports. As I said, Z11 is V1 upon I1, I2 is equal to 0. So I2 0 means we need to create an open circuit. Similarly, Y11 is I1 upon V1, for example, in case of Y parameters. Y11 is I1 upon V1 when your V2 is 0. So this means we have to create a short circuit. So for determining these parameters, we have to either create an open circuit or a short circuit. But it is very difficult at high frequencies, or at higher frequencies, it is hard to create an ideal open circuit or a short circuit. So it is difficult to create an open circuit or an ideal short circuit at high frequencies. The reason is that we have always parasitic capacitances, and because of parasitic capacitances, it won't be possible to create an ideal open circuit. Likewise, it won't be possible to create an ideal short circuit as we have finite inductances. So this is advantage number first. Rather, this is first reason for using S parameters at higher frequencies. Second reason would be, so far as open and short circuits are concerned, under open and short circuit conditions, many active devices would oscillate, or many active devices oscillate and can damage which can damage the device. As you know, open and short circuit conditions, they result in creation of standing waves which can result in oscillations, or for that matter that can damage the device. Another reason, third reason, is for non-TEM modes. Non-TEM modes would mean, for example, transverse electric, transverse magnetic. It is not possible. It's not possible to measure voltages and currents. We only can measure power from we only can measure power one second we can measure power from E and H fields. So for non-TM modes, as I said, transverse electric, transverse magnetic, it is not possible for us to measure currents. Rather, we measure what? We measure the power from electric and magnetic fields. So even if we try to find Z parameters, it would be difficult for us, rather impossible for us to measure Z parameters, as we are not able to measure currents for non-TEM modes. So hence we need a different set of parameters which, number one, do not need open and short circuit conditions. Second, they relate, instead of voltages and currents, they relate incident and reflected waves. Instead of voltages and currents. Now let us see what are the advantages of using S parameters. Advantages of using S parameters. First thing is, they are easy to measure directly. Easy to measure directly. For example, we can use a vector network analyzer for measuring S parameters. Second advantage is that these parameters, these S parameters, they give useful information. They give useful information about the properties of components, used at high frequencies or microwave frequencies. For example, S11, if we measure the parameter S11, this gives us the reflection coefficient directly. S11 gives us the reflection coefficient, provided the other ports are matched. So this means, say for example, I have a two-port network. This is port 1, this is port 2. So here we discuss incident wave, and then the reflected waves, reflected wave, reflected wave. So incident we designate by A1, incident A1, A2. Reflected here would be at port 1 B1. This would be reflected B2. This is your port 1, this is port 2. So S11 is reflection coefficient. See, S11 is simply B1 by A1. So if we measure S11, that gives us the reflection coefficient. Reflected by incident is your reflection coefficient. This would be your reflection coefficient. Provided the other port is matched. That would mean this has to be this at port 2. As I said, S11 by definition is, as I said, S11 is your B1 by A1 when your A2 is 0. So what does that mean? That means you can find the reflection coefficient directly from this ratio B1 by A1 provided your A2 is 0. That's it. So this is advantage number second. So the first advantage is they are easy to measure directly by using devices, for example, called as vector network analyzers. These parameters, they give useful information about the properties of the components used at high frequencies. For example, S11 is simply the reflection coefficient. S21, for example, what is S21? S21 would be B2 by A1. This B2 is this wave, A1 is this wave. So B2 by A1 simply represents the gain or loss, the ratio of output to input. So it simply represents the gain or loss. So that's what I said. These parameters give useful information about the properties of the components used at microwave frequency. So this is all for the day. Good day.